Hello and welcome. Here we have a mixing chamber where a superheated ammonia and a saturated mixture of ammonia uh, mix together to produce a saturated vapor. So we have state 1 would be our superheated ammonia, state 2 will be our saturated mixture of ammonia, liquid and vapor, and finally state 3 will be the exit state of saturated vapor. Some of the properties of these three states are given. It's an adiabatic mixing chamber, so we'll assume that there is no heat transfer, so Q dot goes to 0. Also, pressure doesn't change, so P1, P2, P3 are all going to be the same at 200 kPa. And we neglect Ke and Pe to determine the mass flow rate of the saturated mixture. So question is, what is m dot 2? So we have the flow coming, m dot 1 is known. How much should be m dot 2 so that we meet a desired exit state? We'd also like to find S dot gen of the universe, that is, what is the amount of mixing friction as quantified by entropy generation of the system's universe. Well, these concepts are covered in chapter 4 in your textbooks, and 6 also covers the exergy related portion of that of those devices. Also, if you go to TEST website, you can go under animations and see in chapter 4, for instance, it's a multi-flow mixing, and these animations will explain how the governing equation of mass and energy and entropy gets simplified for a mixing chamber. So here is another example of that. So please go over this animation as well as the textbook to understand more about the entropy that is generated by mixing as a fundamental thermodynamic friction. Just to make another note, this particular problem we are going to solve is from chapter 4, and it's on the mixing flows, and this is an example problem, so the solution is available to everyone. You can go see the manual solution, so that'll be a good way to get started. Once you understand the manual solution, the test solution will make a lot of sense. Okay, so let's go over the problem. I have already started the test steps again. How do you start the test step? You go to the test steps page, and it's a system problem. So you go down the it's an open system problem, steady system, and if you go down the tree, then you can see that the mixing problems will be covered under the generic branch. This is a single flow mixing multi-flow system. Once you click there, let me get all these inks out. Once you click there, it will offer you all the different models that are available, and we have ammonia mixing with ammonia. So, and it's a saturated mixture of ammonia, superheated vapor of ammonia. So therefore, obviously, PC model will be the most suitable of all. So we click on PC model to launch the app, which is shown on this tab. I have already launched the TESTapp and entered state 1. Obviously, I selected ammonia as the working fluid, entered the pressure that is given, temperature that is given, mass flow rate that is given for state 1. And because Ke and Pe are negligible, I left the velocity and altitude at their default values of 0. Okay, so regarding state 2, what is known? So you go to state 2. Again, pressure is given, pressure is equal to P1, and it's a saturated mixture of quality being given. So we enter the quality as 20% or 0.2, but the mass flow rate is the big unknown, so we leave it blank. Well, with that, when we go to the state 3, we notice that we know a few properties here. Pressure is again known, is saturated vapor, quality is known, so we can find the entire state, except the mass flow rate is still unknown. And so we enter it as m dot 1 plus m dot 2, as you can see here. And the white background represents that it cannot be calculated. Something is wrong with this expression. Obviously, we don't know m dot 2, so therefore m dot 3 could not be evaluated. So we go to the device panel. By the way, it's always a good idea to go to the graphics panel to make sure the states looks reasonably correct. Yes, state 1, 2, and 3 are all thermodynamic properties are known, and as you can see, they're in a constant pressure line because pressure doesn't change. So 1, 2, 3 are all on one pressure line of 200 kPa. Okay, now let's go to the device panel and set it up. Its a device type is multi-mixing, that is multi-flow and mixing is allowed. That's why we have 4 different states, 2 going in, 2 coming out. But in this case, we have a state 1 and state 2 coming in. You can see that it's being filled up by ammonia, picked up from the state properties. And any of them, either of them, we can select as state 3 and left the other one as a blocked. So in other words, we have just created a mixing chamber. Ammonia comes at state 1 and 2, goes out at state 3. What else do we know? They said adiabatic chamber, so Q dot equals 0, and there is no external work, of course, because mixing chamber is a passive device. Note that the mass, energy, and entropy equation simplified for this device is shown here. Well, Q dot equals 0, so there will be even additional simplification. So that's, as you can see, manually it's easy to solve the problem if you know the properties J and S. All right, so let's go. First, let's do a calculate. What does calculate do is that essentially it calculates the properties from the energy equation, substitute back in the state panel. So all we need now is a super calculate to iterate between states and device, and we are ready now. If you go back to the state, as you can see, state 1 at state 2, now we know exactly what is the mass flow rate. That was one of the desired unknown of the problem. And state 3, of course, will be m dot 1 plus m dot 2 evaluated and posted here. And if you go to the device panel, you can see that the entropy generation for the universe is also posted. So essentially the problem is solved. Another, sometimes a more complex problem, to solve that, you may have to take advantage of iteration. For instance, you could say Q dot is unknown in this problem, and to iteratively solve the problem, you can go and say, for instance, the state 2, okay, we don't know what is state 2. Let me just quickly do that. Suppose we don't know what is m dot 3. We know m dot 3 will be equals m dot 1 plus m dot 2. That's always true. Again, it's white background because I initialized m dot 2 here. So again, I don't know what is Q dot, and 1, 2 going to 3. So there are 2 unknowns here, m dot 2, and we have an unknown of Q dot. So suppose we guess m dot 2. Suppose we say, you know what, m dot 2 is 0.1 kg per second, and calculate the state and super calculate. Come to the device panel, and it shows that to get this particular exit condition, Q dot 1 is 64 kilowatt. In other words, you have to heat up the mixing chamber to get there. So your goal would be to guess m dot 2 so that Q dot 1 goes to 0. And this kind of an iterative approach, it seems like clumsy, but that's how most computer works. So in other words, you want to guess something which will give you a negative Q dot. That means you're losing heat. So then you kind of come in between, so that way you can quickly converge to Q dot equals 0 and get the iteratively the correct answer. So anyways, the what if scenario is quite easy in this particular problem. Go to state 1, and the problem says that what would be the mass flow rate if the superheated ammonia entered at 0 degrees Celsius. So all we have to do is to change the temperature from -10 to 0 degrees Celsius, and we do a super calculate, and we are done.